I want to say thank you to everybody for taking a gamble that tomorrow's weather will be the same as today's, and not worrying that you're going to miss your chance in the sun. So thanks for coming out. We have Dr. Frederick Chester here with us today from the University of Texas A&M. Upcoming lectures we have on Friday at 7, not here, but at the Science Center. We have a talk from the director of SERVS. So if you're free on Friday night, come to that. And next Monday, 7 o'clock p.m. Next Monday at noon, we have a talk about humpback whales, and then to follow that up, we have a video on the Tuesday night about humpback whales. So we have a very humpback-oriented week next week, but it should be fun. So, all right, I'll let Dr. Chester take it away.
Thank you very much. Well, thank you everybody for coming tonight. I know it's hard to turn down the weather, but I appreciate it, and I'm very excited to be here today and talk about something that consumed several years of my life, almost entirely, and is now coming to completion in a sense. And I'm very pleased to be able to talk to you about it. I should mention that I was supposed to come with an outreach person to talk to the schools, but instead they didn't come, so I spent the day at the school, and probably tomorrow morning too, and that's been really enjoyable. And Lance set that up for me, and I really appreciate that, because it gets a chance to talk to a lot of young people, and it's fun. I may have lost my voice though by today, so I'm going to struggle through it. Yes, good. Actually, my talk is a little bit tweaked today. I'm not going to talk too much about the challenge, but more really take the opportunity in light of the 50 years since the Alaskan earthquake to mention that and set up my work, and also just kind of illustrate the main things that we discovered 50 years ago and the things that we're still discovering about earthquakes and subduction zones. It's pretty amazing that we still know so little, really, about. I mean, we know a lot, but we're still surprised, and I think you'll see that today. I was on the expedition and helped organize it, and that was a great honor to be asked to be co-chief, and it was probably one of the most rewarding things I've done in my career. Although I've done a lot of different things that are very rewarding, but it was something else. Anyway, to set it up, as you probably know, 19 of the 20 largest earthquakes in recorded history, which really is over the last 100 or so years, when we had instrumentation and could measure these things accurately, 19 of them are in the subduction zones and around the Ring of Fire, associated with large volcanoes of subduction systems. And these are definitely the ones that release the large amounts of energy, and on top of that are the ones that to create tsunamis, which really turns out to be really the most devastating component of the large earthquakes. The shaking is extreme, and there's other consequences, but the tsunamis take lives, and as we've seen with our modern infrastructure along coastlines, it's economically disastrous as well. The four big ones, Chile and the Alaska event, and then the Sumatra and Tohoku, these last two very recent in our minds. I mean, it's just pretty amazing, and of course we see it because of modern media and communications. We see it real time, which it really is remarkable to see these things and look at the power of the Earth as exhibited. I'm going to talk about the Alaska event and the Tohoku event. They have some similarities, but also some major differences. And the Alaska event occurred at a time right when the plate tectonics theory was being developed. So we were constructing that. That was actually before I was in college, really. But it was an amazing time in geology, because all of a sudden we had a theory that really explained so many things: earthquakes, trenches, rifting continents, subduction zones, volcanoes, mid-ocean sea floors, but everything just was coming together. And then, as that was happening, this 1964 Alaska event occurred, and it was so remarkable. I mean, geologically speaking, And as a consequence of certain aspects, like the fact that the coastline is so intricate and many islands, some the geologists at the time were able to measure uplift and subsidence, and that data, as I'll show you, is kind of like a characteristic is observed in all these events. Told us a lot about subduction zone earthquakes, but that they fit within plate tectonics and actually supported the whole theory of plate tectonics. So that was a very important event geologically and in terms of geological science. I'm going to touch on, oh, I'm sorry, I knew I was going to do that. Let's see, can I go backwards?
Yes.
Yes. Okay, so I'm going to talk on these again. The other thing that was observed is that almost the entire Aleutian arc ruptured in a very short period of time and filled in these spaces as one occurred, neighboring ones occurred. And this tells us, and which we know, although it's not as dramatically obvious in this case, in all cases, but that earthquakes, as they slip, they do release stress, but they pass it on alongside, and it can lead to cascading or even linking of segments that once ruptured independently. Now we know they can also combine and make larger earthquakes. And that's a difficult thing to predict, and it's highly nonlinear and variable, but it does occur. So that was an important realization. And then, of course, it led to the earthquake hazard program, which was very important in terms of understanding and mitigating earthquake hazards.
What are the blue dots on the map?
These are earthquake events, and this is, of course, the Alaskan rupture area. And we'll come back. I'll mention this later, actually. The Yakataga Gap. Okay, you're probably all familiar with subduction zones and the geologic concept, and I see this is a part where I won't be able to trigger the video, but we don't really need it here anyway. Yeah, this is a block diagram showing the seafloor subducting under an island arc at a trench, and you can see the downgoing slab. And this is a cartoon here that's basically of this side that's relevant to Japan as well as the Alaskan Aleutian arc. And the idea is that it's at divergent margins within the seafloor is spreading and creating new oceanic crust by igneous processes. The mountain chains through the oceans constitute the largest igneous province in the world. And then these plates, due to convection and their own increase in density, drive subduction. And so they convey along and then subduct underneath the island arc. And there's a characteristic sequence of sedimentation that tends to occur, and as they get to the trench, there's also sediment that's transported on from land, and that much of that is accreted or scraped off. And then there's the contact between the overriding plate and the subducting plate, which is very much a frictional contact, and this is where the great megathrust earthquakes occurred, from about 35 kilometers depth to about 10 kilometers depth, typically. And this is the elastic rebound hypothesis, which was actually developed earlier in the early 1900s, applies to the seismogenic thrust events as well. And this cartoon, which is very cartoon-like, but it illustrates the concept that at the locked portion, this is a frictional fault, and long turns that become stuck. And so as the subducting slab continues its steady progression downwards, it hangs on to the overriding plate, and it causes elastic bending and distortion of the overriding plate, which leads to subsidence in the very usually under the ocean part touching the plate, and then uplift behind that, slowly generating over a long interval of loading the fault. And then when the earthquake occurs and we exceed the frictional strength, and this slips suddenly, and then we're exaggerated here, but in the frontal part of the accretionary prism, this pops up and there's uplift, and but behind in the lower parts of the slipping patch, it sinks again. And this is pretty much elastic, so it's a repeated cycle. Yeah, question?
Excuse me, what's the actual angle of that subsiding plate as it subsides? Is it very, very shallow, or is it as abrupt as that?
No, it's very shallow. The slope of it's actually more like a prism, and the mechanical analogy is if you have a bulldozer and pushing sand, or if you have a bulldozer or a snowplow pushing snow, you form a long prism in front of the blade. And you can even, and the analogy here is that even pushing up is achieved because of that prism shape. So the slope of the surface is usually about 5 degrees.
And how about the subduction?
And the subduction is about the same. Now there's some steeper, and it steepens with depth, but not as much, 10 degrees or so over the length. So it's really a very narrow prism. You'll see that in one of my slides later. It's a good question. This is kind of silly exaggeration, but it illustrates the point. And of course, this is elastic, so we have this earthquake cycle where you load and then slip event and then it reloads. So these changes in subsidence and uplift are cyclic. And this stage occurs very slowly over long periods of time, like now in the rupture area of the Alaska earthquake. And then this is what happened right during the earthquake. And this is, as a result, it's kind of an artist's representation. There wasn't this much data out here. We really don't know this actually for a fact, but the general concept is well founded by measurements all along the coastline of uplift and subsidence. And this is a characteristic of all big subduction thrusts, based on and it satisfies the elastic rebound hypothesis. This big uplift and subsidence is what generates the trans-Pacific, tsunamis, these huge tsunamis that can be generated and that were generated in the Alaska event, and of course they go down, to South America as well. There's also, well documented in the 1964 event, is local tsunamis, like Whittier was affected by a very local but high amplitude tsunami that was associated with triggered submarine landslides that displaced the water and then threw the wave, drained the bay, and then threw the wave up on into the town, and it happened actually right at the end, or right before the shaking of the main earthquake actually stopped. So it was really quick because it was so local and such high amplitude. That happened to other places as well, and we now know that there's a number of different kinds of sources of tsunamis. This is, of course, the big regional one is the broad uplift, but there's local phenomena that can be just as devastating and important for hazards. And of course, they're powerful when the water's moving and it's carrying debris, like shown in that picture from the Whittier tsunami. Okay, so I'm sure most of you are familiar with the Tohoku event. It happened on TV practically, watching it, and the devastation was just unbelievable. Even like the Alaskan earthquake, most of the damage and lives lost was due to the tsunami, not to the shaking, even though the shaking was major shaking. And in the case of Japan, the best prepared country for tsunamis and earthquakes, their engineering effort, they have a real-time warning system, although it sort of failed on this event because it was so large and exceeded anything they expected. And by the time they got and also because they had set up a procedure to be very safe and conservative about this, releasing the warning to the public. And so by the time they actually released it, most people had already made their fateful decision whether they were running to high ground or not. So, yes, question?
What would be considered an indirect cause?
Indirect cause is probably like someone that died as a consequence of some event from, like for example, dying of radiation poisoning from the leak, something like that.
Was the leak a result of the earthquake?
Yes, it
Oh, I
was.
didn't know that. That's amazing.
Yeah, the radiation release and the meltdown because, well, we can talk about that later if you're interested. So, yeah, there's other indirect causes as well. And of course, this was, like I mentioned, very costly as well as a source of lost lives. And the plate tectonic setting is pretty similar. I mean, it's basically a subduction zone. The difference is that there's not as much sedimentation off the land, and so the trench is rather bare. And there's ideas about different kinds of subduction zones, and we have erosive and accretionary. I'll mention that in a minute. But anyway, the rates are a little bit higher. Half again is more than here in Alaska, and it can generate a magnitude 8 every 100 years or so at that rate. And interestingly, there's a long record there, 400 years, and this is what's observed, 13 magnitude 7s and 5 magnitude 8s, and we pretty much recognize that that's sufficient to carry and accommodate the motion of the plates. But it turns out that we weren't aware of the compound nature that could be created in this particular event. And I'll talk about that in a minute. So really, there was not a magnitude 9 expected. It's not represented in the last 400 years. And it generally was not expected, although in hindsight, there were signs, and we probably would have figured it out before it happened if it had waited a little bit longer before taking place. And this is an example of some of the thinking that was happening. This was published in 2010, for example. And this was kind of our state of knowledge. We were recognizing that the really great large earthquakes were associated with what we call a accretionary margin. That's with a lot of sediment and a big accretionary prism. And the Alaskan event, the now understood Cascadia event in 1700, Sumatra, these, and Chile, they're all associated with big accretionary margins. And then there's the ones that are more barren, which we call erosive, and I won't go into details about that, but they tend to have these other kinds of earthquakes, also that generate tsunamis. In fact, we call them tsunami earthquakes. And they're characterized by ruptures that are actually very out deep, close to the trench itself, but they progress slowly. So the earthquakes seem very small, but they generate enormously large tsunamis. And they tend to be associated with these erosional margins, and they're by the green dots. Well, what happened is the Tohoku earthquake is a compound event. It has basically all the signatures of like the Alaskan earthquake, the deep rupture with large coherent irradiation in a short period and very large magnitude. And on top of that, it has the tsunami characteristic as well together, and which is why it creates such a large earthquake, even though its rupture length is only about half the length of the Alaskan event. And this was a surprise to us. We didn't understand that this could happen. However, just 10 years earlier than this event, workers had started carrying out excavations looking for tsunami records or records in the sedimentary sequence. And these characteristic tsunami deposits were being trenched and mapped. And they realized that there was a large run-up here, and it correlated with a written record of a tsunami, a large tsunami, of the Jogan event in 900 AD. And so they trenched and found a signature of several of these. And this led them to conclude that over an interval of 8 to 1,000 years, they have these large tsunami events. And it was modeled as a tsunami earthquake, that is just the rupture out deep near the trench, not a very large rupture, and not tied to a great earthquake that we'll see is what happened in the Tohoku event. So there was signs that a big tsunami and a tsunami source could be anticipated, but even this doesn't anticipate the combined event. This is really the best instrument. I can't show you all the data that we have that document what I'm about to tell you. And that's that the slip distribution on the Tohoku event was a record-setting in many respects. The best evidence is from the tsunami itself. These are pressure gauges, records, that are offshore about halfway out to the trench. And there's a couple of them. And what they do is as the tsunami wave moves past, then the seawater height is higher, so it increases the pressure. So this is actually a time record. You can see at this location, here's where the tsunami wave starts to hit. That's actually the earthquake. And then as the wave moves inland, the pressure goes up. But what's interesting is this is the broad tsunami wave, much like what is produced typically for a broad uplift region. But riding on top of that is this spiky additional wave. It's like a wave sitting on top of a wave. And because of all the records, the pressure data, and also the buoy data, and then the well-documented arrival on shore, which can all be worked out, they can invert. And this is a map. This is like a digital version of the slip, the fault surface itself and the slip zone, trying to calculate where the tsunami originated. And this spiky peak originated right out at the trench, which is unusual. And the broad region represents the whole region itself, the whole slip area. And so this really effectively increased the size of the tsunami to 40 meters run up and inundation, compared to the Alaskan earthquake, which was more like 8 or 10 meters, which is also a sizable tsunami, but not like the one in Japan. And this slip out to the trench in these models comes to about 40 meters. Now, nowhere has we seen anything greater than about 20 or 25 meters, and that's usually in the epicenter area. And most earthquakes, if great subduction earthquakes, the slip decreases as you get towards the trench, and there is no slip at the trench, or that's what we think. But the Tohoku event, the slip increases in magnitude right out to the trench. And now we know it's actually more than 40 meters from other kinds of data. It's more like 50 and maybe even 60 meters in some places. That is a phenomenal amount of slip. And it's consistent with only this kind of event occurring every 1,000 years or so, because it takes that long to build up 60 meters of slip. So Japan, some 10 years ago, built a science drilling, a deep water scientific drill ship, part of the Integrated Ocean Drilling Program, their platform, specifically to carry out research associated with earthquakes, but also other problems too. And this enabled us to carry out deep water drilling. This is a modern, ship that's based on petroleum drilling, exploration, deep water drill ships. It's really a phenomenal. And on top of that, it has all the equipment to take core samples and a big science stack. And the laboratory, the science laboratory on ship is unparalleled. It's just a really amazing vessel. And after this event, the Japanese government and the drilling programs pushed to be able to do a scientific experiment, and that's what happened. And it's really motivated by this, that maybe we can do better and mitigate more if we have better understanding. And we also wanted to understand, of course, what happened in Japan in particular. But we also wanted to address some other long-standing questions in earthquake physics, and I'll mention that in a minute. I should just also give a nod to scientific ocean drilling history, which began a year after I was born, actually. Not that there's any coincidence there. But that was with Project Moho. Maybe some of you have heard of this, and it's being talked about again, trying to drill to the Moho or the mantle. But I like this because it's a picture of the barge, real roughnecks, not the automated system that I saw on the ship, and also a story written for Life magazine by some fellow named Steinbeck. Maybe you've read some of you. Ocean drilling program expeditions are typically this. They go for 2 months. They're driven by science proposals. They take several years and iterations in order to get the science strong enough and well conceived enough to warrant an expedition. And it involves about 24 scientists from around the world with all different specialties. Many expeditions have a main focus, but other disciplines also have problems that they can address. And so it's a big team of scientists, similar size for running the drilling operation, and then the ship, the crew and maritime crew. And so the typical ship has about 100 people total on the ship. The primary focus in ocean drilling is usually taking core, and they usually drill holes with just core all the way because they want the complete sedimentary record in the seafloor, and what is it's a slow, methodical process. You get about 30 to 60 meters a day, so to drill several deep holes, say 1 kilometer deep, takes a couple months in duration, and it works around the clock to 2 teams with 12-hour shifts, 7 days a week. And the secondary focus, and more recently an important focus, is using borehole geophysical logging data, like they use in the oil industry, to make indirect measurements of what you're drilling through. And also establish borehole observatories. These are instrumentation that you stick down in the borehole and either leave there or retrieve the data somehow. And this is becoming more and more common, particularly in tectonic-related types of problems, like this one is, related to the earthquakes. And this expedition we did, JFAST, is really multifaceted in that it included all 3 of these elements in one expedition. It was unbelievably ambitious, silly in a way, to try to do so much. And on top of that, it's a rapid response expedition. This is a first in scientific ocean drilling, is to carry out a rapid response drilling expedition. And this is because, as implied by this figure on this report, white paper that was written just several years before the earthquake event, about the advantage of making a rapid response a scientific drilling project into a fault that had just ruptured. And the reason is because right after rupture, the rubbing and the frictional processes of slipping generates heat. And by going there immediately after drilling, we have a chance of measuring the amount of heat that was released by the earthquake. And by that way, we can answer the very fundamental question about how, in an absolute sense, how strong the fault is. We have no way to do that otherwise. And so this was part of the motivation, and because there was a science plan in place, we just used that, but actually it was written for the International Continental Drilling Program, because it seemed inconceivable at the time that one could do it in the oceans. But in fact, it turned out that the ocean was, because of the huge event in Tohoku and the ability just barely to drill that deep, we could attack it in the Tohoku event. So our plan was to use logging while drilling, geophysical measurements in the first hole to determine where the fault was, and also measure the in situ stress, which I won't talk about today. Then the second hole to take core samples and bring them back to the laboratory so we could do all kinds of experiments to learn about faulting. And then the third was to place this temperature observatory in a third borehole across the fault so we could measure the frictional heat. And I'm going to talk about that in a minute more here. You know, because it's an elastic process, we actually know from the amount of slip and the elastic properties of the lithosphere and the stress drop, we can calculate what the stress drop is. That is how much the stress changes from when it's just about to break, this is just force per area on the fault. How much it's about right when it starts to slip to what it ends up being at the end of slip. We can determine that. What we can't determine is whether the average friction or the average stress is high or low. This has been a debate ongoing for a long time. Recently, a number of more recent observations are suggesting that these big plate boundary faults actually have low average frictional strength. But there's no way to test that, and that's what the main goal of this one. And in order to do that, we had to get out there and drill fast to get the signal. And so this was one of the main questions that drove our expedition, in addition to just learning about Tohoku in particular. And you can understand this with the rubbing the hands experiment, which I know you guys rub hands out here because it gets cold in the wintertime. And you rub your hands to warm them up. And you basically release the mechanical energy and overcoming friction, the frictional force. You're doing work which dissipates its heat on your hand and warms your hand. Turns out, you know, to get 50 meters of slip, you'd have to do this for well over a minute. And I have never been able to get past about 5 seconds. And on that, you have to push really hard, too. And even our pushing, we can only push about 1/10 as hard as occurs, or even less, actually, as occurs on a real fault zone, even as shallow near the surface of the Earth. But you can feel the warmth. And you can also imagine, if you have done this, that if you put lotion on your hands right before you go out to warm them, you know, because lotion lubricates, you can't generate the same amount of heat, it turns out. And the harder you push, the hotter it gets. And these are all understood in terms of physics. And so if we have a way to measure the amount of heat, Q, which is what we do with measuring the temperature, and knowing the displacement, which we know from seismology, and the fault area, then we can calculate the frictional strength of the fault, which is this question that we're trying to answer. Now typically rocks, when we slide them slow, they're pretty high friction. They're pretty sticky stuff. Compared to metals, they're higher than metals. There's some exceptions. And at this high friction, it's much analogous like your brakes. And you know if you ride your brakes, they heat up to the point of actually destroying the brakes. So rocks are expected to heat up significantly at that level of friction. However, in nature, there's some other processes that can be kicked in at large earthquake slips. And the friction is thought to be able to drop to less than 0.1, which is pretty darn slippery. And the hypothesis is this might be important for these really big earthquakes. So that was one of our goals, was to determine if it's that weak. This is an experiment in the laboratory, and amazing it worked, I guess. Is it going to work? Yes. And this is a rotary shear experiment. It's like a lathe, but it's designed to slip at earthquake rates. And if you count 3, 4, 5, 6, 7, 8, 9, 10, that's 50 meters. And you see that it's melting the rock. So if it's high friction, and this is about the right normal stress as occurs in the Tohoku event, then we would expect to see glass on that fault.
That's pretty cool.
Yeah, that's pretty neat. Well, we don't have the one video I have that has audio. This is the one because you hear the. This is in the new machine in Italy, and this was like one of the first experiments. And as you saw, when it starts to melt, the two pistons start coming together, and they were freaking out.
What
Stop,
sort
stop,
of rock?
stop, stop.
What sort of rock was that?
That was a diabase, which is like the basalt of the igneous rock of the crust. This experiment was dry, it's at room exposed, and so it's not exactly the same as as occurs in nature. In particular, we don't have water, and we don't have fluid pressures. All these things can contribute to weakening. So it's not really a perfect test, but it does illustrate high friction leads to melting. Okay, I'm just going to mention this. From the earthquake event, 13 months later, we were in the water sailing to the site. It is absolutely unbelievable, and that we could get everything, and particularly since we had to actually build the observatory, have things made. We had a lot of untested equipment that we had to just put on the ship and go out, and we had a lot of problems because of that, and also bad luck in a sense. And but in the end, I'll show you that we actually achieved our goals, which is really remarkable. This is the vessel that's capable of two kinds of drilling. Riser drilling is what is used in the petroleum industry and allows them to drill very deep and control, and by pumping the mud down, which removes the chips, and then pumping it back up onto land or to the pump, they can control the mud weights, which allow them to pressurize the borehole enough to keep it open as they drill very deep. You can only do that in 2.5 kilometers of water depth. If it's deeper, then you can only do non-riser drilling, which is where you pump the seawater down, and then the seawater washes the little cuttings of rock or sediment and dumps them on the sea floor. In this case, you don't use any fancy fluids, or you don't control the mud pressure or the mud weight. You're just using seawater. And so that means that the pressure at the bottom of the hole is limited in magnitude, and that means we can only drill about 1 kilometer deep. Our water depth was 7 kilometers, which is remarkably deep. Never been really achieved before, and the expedition was set a record in that respect. And it took all the knowledge and technology in order to achieve that. This is a cross-sectional view of our drill site. This is the igneous crust of this Pacific plate that's subducting underneath, actually the North American plate, if you can believe it, in Japan. It wraps around, and the northern part of Japan is actually considered part of the North American plate. Actually, now we have 56 different plates and even more mini plates and micro plates. And so, in that sense, it's actually a different little plate, but the first order approximation is part of North America. Anyway, here's the plate coming underneath. It has about 450 meters of sediment sitting on top, very characteristic sequence of sediments. And that gets scraped off, and this is starting to build the accretionary prism here. And because of the bending of the plate, you get this Horst and Graben structure. Maybe some of you have heard of that before, but anyway, some faulting and some irregularities. And this is the basal thrust, or at least what we anticipated before we went out there. And then later, more seismic data and our drilling result tells us that this is the structure of the subduction thrust. And we had a 7 kilometer depth limit. We had to drill shallower than 7 kilometers, but we needed to hit the fault at 800 meters or so depth in order to get enough normal load, to get enough frictional heat that we could measure it. And so that's this window right here. So really we had about 1 kilometer section in order to achieve our goals. And this is for scale. The ship is, well, that's actually a little big for the ship. The drill stem is remarkably long. And this is to scale 1 to 1. So you're just seeing the very frontal prism. But this is where the large slip led to big thickness changes in the sediment, and that's what generated that spiky wave. The ship is just amazing. One thing you may wonder is how on earth can you hold a ship still in the waves? And it's got these azimuthal thrusters and big under the hull thruster. And as you're drilling, these are just kicking on and off. You just get used to these things roaring up to keep the ship in drilling. When the first expedition I went on the Chikyu was in the Nankai Trough, it was actually in the Kuroshio current. And so it was about 3.5 knots of current. And this ship just held its place and continued to drill. Amazing. And we also positioned the ship by dropping transponders. We had only 6 transponders that can operate at 7 kilometers depth. And by the end of the drilling, all but 3 were working. I mean, were failed. All but 2. I mean, we only had 2 at the very end that didn't fail. And it's supposed to be able to send a signal and they recover to the surface, but in fact, we didn't recover any of them. The water depth really pushed our technology in order to achieve this drilling. And not only that, it wasn't just drilling deep. We had a really complicated drilling plan because we wanted to put an instrument in the borehole, which means that in order to do that means you have to re-enter the borehole. In order to re-enter, you have to put a wellhead on with a receiving cone. So the first step is to attach on the bottom of the assembly is to put this wellhead, which is about 30 meters of 2-foot diameter pipe, and this little cone on the top. And so we had to push that in, and then what I had learned, the hard part, we had to let go. First time we didn't let go, it wouldn't let go, and we ran into problems. We finally worked that out with engineering on ship and modifying some components. This is the tool that's called the running tool. This is releasing the wellhead successfully in hole C. That was our third try. And then after that, you release that, you pull the drill stem up. It takes 36 hours just to deploy the drill stem and 36 hours to come back up. So anytime we had a failure, we lost a week. Turned out by 4 weeks into the 2-month expedition, we hadn't accomplished anything except a lot of failures. Although that was the learning process, and later we were quite successful. Then you put on the drilling assembly and the logging while drilling tools, and you re-enter the cone, drill a hole, and you pull out, and then you again establish a new bottom hole assembly. That's the instrument stack in this casing. You attach that to the drill stem and you insert it again into the hole. That means we have 2 re-entries and 2 releases for every one of these holes. And that was a remarkable achievement. Up here, I don't know if I can get this video to work, but I'm pretty sure I'm just going to advance on this. Yeah, but you would see the drill stem fumbling around until finally it drops in.
I can go back and
Oh, it's not
I'll
that
click your
important.
video.
I'll show it afterwards.
Okay.
And then, of course, you have to recover the observatory after you place it, because we let it sit there for 8 months. And that was key to actually making measurements. I'll show you that later, to be successful in the temperature measurement. And we did that with a very deep water capable ROV, the Kaiko, which can go 7 kilometers. We will stop for that video. And so I'm really going to just blast through some of the results. The first hole, we did collect our geophysical measurements, and that was a month into the expedition. Here's an example of a well log and an image log. And by looking at those signals, we were able to identify 2 targets for drilling for the fault, one of which we favored, and then the subsequent hole, we cored both of those. And we collected 9 cores, or about 10 cores, across the lower target, 850 meters below, 820 meters below the seafloor, at 7,000, 700 meters below sea level. And not only that, we recovered a core from the fault itself, which was absolutely amazing. This has got to be the rarest rock, rarer than moon rocks, and, well, pretty expensive also. Maybe not quite as expensive as a moon rock, but, you get the idea. Probably per pound, it probably is more expensive than the moon rocks.
Where is it now?
Pardon me?
Where is it now?
It's most of it is cut up, but there is an archive half. There's a few sections that are missing, but there's an archive half in Kochi. The ocean drilling program always cuts the cores in half and then preserves half in the repository so people can go and inspect it later. Now some of it was sacrificed to get hole rounds, but even then I think probably some of that will go back to the core center and it's preserved. They also made a replica for, it cost them $10,000, but it's beautiful. It's beautiful.
Is that basalt?
No, actually I'm going to talk about, this is a piece of mudstone here, and then this is the fault rock itself, and it turns out to be a scaly clay, which is kind of surprising because geologists typically, when they see scaly clay in fault zones, they interpret them as aseismic, creeping faults. And this definitely ruptured in a big earthquake. Here actually is the coring run, and we usually take 9-meter coring runs, but we were only recovering about 1.5 meters or 2 meters. And so we knew where the fault was based on the geophysical data, and so we wanted to make sure we captured that. So we shortened our coring runs down to 3 to 5 meters, and you see we got about the same recovery. This material is so weak and friable at this depth, it's really sediment more than rock, and it's all deformed, and so it's very delicate. But we did capture a 1-meter section. This is the CT scan, CAT scan of the core. And you can see these pieces, then the mudstone, and then some other layering in here. That's the scaly clay. And then these are photographs. And this one in particular was quite exciting because this contact, based on studies of faults on land, suggested that this was the surface that slipped in a major earthquake like the Tohoku event. We don't know if it slipped in the Tohoku event, but probably an event like that. This would be the characteristic feature we would expect to find. And just recently, using transmission electron microscopes, studying this material, they find traces of melt. And the only way you could have traces of melt is if it was a seismic slip rate. So that was very exciting. We did capture the surface of an earthquake in this core. And it turns out, later I'm going to show you the observatory confirmed that this is the fault depth that generated the heat anomaly. So we captured the fault and verified that it was the one that slipped by the heat anomaly. So it was a really amazing result. An interesting thing, the scaly clay, where did it come from? We hypothesized that in the characteristic sedimentary sequence, this is a core that was taken drilling expedition some 25 years ago out in the Pacific Ocean, not at the trench, not in the subduction zone. And so this is like the incoming sedimentary sequence, 400 and 450 meters. And it has a characteristic lithology, and at the bottom is this pelagic clay, which is very old, because it's old oceanic crust formed right after, out in the deep sea. And it's very rich in clay, in smectite actually. And we expected that this could be the horizon that the fault would take advantage of. What we found, and only by using, because there's no fossils in this, only by using geochemical fingerprinting, we could find out that this was in fact this horizon. Now in the incoming sequence, it's 30 meters thick. In this sequence that we drilled, it's only about 2 meters thick. So the fault apparently took advantage of this clay and then used it or smeared it along the surface throughout, even where that clay didn't exist because of the unconformity in the sedimentary sequence there. So it's a quite interesting result, and that the clay was, we know clay is weak, but that it was activated and actually transported and tectonically placed along the fault where we drilled. And we anticipate that this is probably pretty efficient at smearing it out along the fault surface everywhere, although that is a hypothesis that should be tested. And finally, I want to show the observatory. This was the scheme of the observatory, which was basically very sophisticated, a rope, 800 meters long, with a big hook on the top. There it is. There's the hook, the hanger, and there's the wellhead. And then on that rope, we tied these sensors. There's little ones here and also big ones, 2 different kinds, by 2 different suppliers. And they have somewhat different capabilities. Some measure pressure as well as temperature. All of them measure temperature. They're pre-programmable, and the data is stored inside. They had to be made out of special titanium cases, pressure bombs, in order to withstand the pressure, which is incredibly high at 8 kilometers depth. And they're tied to the rope. And so the idea was we lowered this in the casing with the rope and assembling all the sensors in it. So we assembled this on board and then lowered the whole thing and then stuck it back in the hole and left it there for 8 months. In order to get it, we have to look. Oh, maybe you can show the video.
Sure.
If you just take the clicker and click on the movie.
The bottom part here?
Yeah, just on the movie picture itself. And what you'll see is, well, you won't see us locating. It took 3 trips out to finally locate the wellhead, and we finally located it. And then you have to use the ROV. If you click on that, there you go. Thank you. That's good. And you'll see the arm of the ROV. This is after hours of actually looking. But anyway, they finally found it. And then here's the ROV, the manipulator, one of the 2 manipulators, coming up to grab onto the wellhead so it could hold steady. Then it used its other manipulator to actually grab onto the hanger. It's the hanger. I have just taken out the key clips. This was a long movie to find these clips. And then the other manipulator then lets go and grabs onto the rope, to the rope that's on the ROV with a hook, so that it can use that hook and hook it onto the hanger. This is much like watching things on the space shuttle. It's all so remote. You know, someone's operating this thing on the ship 7 kilometers away. And then this thing just motors up on its own power. It has the capability to lift just enough to pull this thing out of the casing. And this is where it starts pulling it out. And then they retrieved it on board. And there was joy throughout the scientific world. And this is and I haven't shown you all the data. I'm showing you the, kind of the final reduced data after
Thank
taking
you.
all those, there was 54 instruments. We instrumented both faults that we actually sampled, even though we were really confident about the lower one, just in case. And so each one of these is an instrument. Each one of these is the instrument, and this is just averaged over the interval between instruments. So we had instruments about every meter or two right at the fault, at the key area. And what you see is a record of temperature versus time for the, now this is just the first half of the deployment. Actually, the next half, we got more data, which I'm not showing because this is just, I don't have time. And the data is really remarkable. There's some really interesting features in the rest of the data, but anyway, this is the data. We had to recalibrate. We calibrated all the instruments before we sent them down, and then we calibrated when we got back, because what you see is the temperature, and this is the heat anomaly, and of course we colored it red. This is the heat anomaly from the earthquake, and this is at the same depth that we retrieved the core from, of the fault material. And then this is the heat anomaly, and you see the magnitude is only 0.3 degrees Celsius above background. That's how small the heat anomaly is. And it's because even though it occurred on a very thin surface during the rupture, we think, but by the time we deployed it, it has diffused, tens of meters away from the site, or at least a few meters away. And this is the model, the simulation, taking into account conductivity of rock properties and so forth. And it's a remarkable agreement with the data. These are probably just instrument variability. And also we learned, turns out in December, in the middle of December, there was a relatively large aftershock right under the site that caused strong ground motion. That freaked us out because we thought maybe there would be a landslide and cover up the observatory, which when we couldn't find it the first couple times, we were really worried, but we stuck to it. And found it and recovered it. And at that earthquake, some very interesting things occurred. In fact, some of these little heat anomalies like this turned off, and some others turned on. And we use that now to identify how much of the heat transfer is by advection and how much is by conduction. It turned out the conductive anomaly here associated with the fault was rock steady, but these other little ones that perturbed the signal were variable, and the earthquake kind of shook the ground, so to speak, and kind of turned on and turned off some of those small fractures that were conducting or allowing it water advection and heat transfer. The bottom line is the average coseismic friction coefficient is about 0.08. It is very weak, as we hypothesized. And this is an amazing result. And then the additional results associated with understanding fluid flow and associating with the fault, which also turned out to be kind of against what we thought. We thought that the fault would be very conductive to fluids, and in fact, it's really tight. I'm going to leave it at that. I am going to say one thing now back to Alaska, because there's a couple things that we learned now that apply to Alaska and the situation here. This is what we call a slip inversion model. Now, the data wasn't quite as good in Alaska, so the inversion is not as accurate as we can generate now, particularly when we have a lot of instruments like in Japan. The models are very accurate. And they use the seismic energy radiation and model the fault as a series of little patch sources, and they can determine not just the total average slip, but the slip on each of these little patches that contribute to the total seismic energy radiation. And what we found, and this was recognized fairly early on in the Alaska event, although it's a little more elegant here, and it's combined with also subsequent measurements that tell us about creeping movement after the earthquake at deeper levels, which also is consistent with our understanding of faulting, that they go further down, but they creep aseismically between earthquake events, whereas this part is the stuck part. And so, but what we found is areas which we call asperities, where there's a lot of energy released, compared to other areas where there's actually no energy released, or very little. And these basically correlate with the magnitude of slip. So there's a large slip asperity here, right below Kodiak Island, and then there's also a large slip asperity here on the southeast side of the Kenai Peninsula. And then this gray area is just representing the fact that there's a splay fault. There's another fault that comes more steeply up. It actually goes through Montague Island and led to some very large uplifts at that location. But in a general sense, there's a lot of energy released in this patch. This is modern data. It's derived from GPS measurements that are measuring all the time the motion of the plates locally. There's a station right up on the hill in Cordova that contributes to this data, but there's a number of other measurements around. And the people at University of Alaska, mostly Freimuller and his students, have analyzed a lot of this data. And this is showing basically where on the subduction zone the fault seems to be stuck and being loaded. And so this patch right here, which is now being reloaded, that is, this is a sticky patch, and so so the loading is, and the stress is increasing here, and that's causing local deviations in the distribution of motion on the surface, which is how they can invert for this using GPS data. That corresponds with this patch, and this one here corresponds with that patch of the Alaska earthquake. So the places that released a lot of energy during the earthquake are also now storing energy at a larger rate than the surrounding areas. So that's a very important result. It turns out that in hindsight, looking at Tohoku, where Tohoku ruptured, before the earthquake, they were seeing a patch, this kind of concentrated loading in the place that ruptured in the Tohoku event. So this correlates with the places of the fault that are being stressed. This was the location of another rupture, I think the 38 rupture, right here. And there's a seismic gap here, and then the other seismic gap in Yakutat is right here. And what you see is that that is being reloaded. So this is very good information that the event, that this is, it was what we call coupled, and so its loads are being increased. Now, an interesting thing about this is this rupture is a magnitude 8 in 1899, a very large earthquake, and it's been about now 100 years. So at these rates, it's gathered about 5 meters of displacement capable. And on top of that, it occurred before the Alaskan earthquake. And what we know is after a big event like the Alaska earthquake, it will advance the clock on the neighboring sections because a lot of the stress that's released is actually transferred to the margins. So that means this patch was actually probably loaded extra by the great 64 earthquake. So this is a very much a concern in terms of probably if one was to forecast that this would have a higher probability of rupture of a magnitude 8 than other sections. And that's not to say that you couldn't get a magnitude 8 in some of these other locations. That's about the size of an egg. And the other interesting thing is this is the inferred rupture patch of the Alaska earthquake, and you see that here's the trench. So this section right here apparently did not appear to rupture in 1964. Now, we don't really know that, but that would be very much akin to the part of the Tohoku earthquake rupture where it was loading more deeply, not loading at the trench, and yet it slipped at the trench in this one of these longer recurrence interval events. And so it's not inconceivable that other earthquake zones like this, that you have these big ruptures, but this part doesn't necessarily rupture. Now, we don't know this, I should say, but what I'm really leading up to is there's a lot, and some of what we've learned from Tohoku, it makes us be suspicious now of the possibility of a tsunami earthquake out here. And you can see that in this model, that is being loaded. Now, I should also caution you that with the scarcity of GPS data stations, the models could be better. And we don't have the density of stations like they have in Japan. So the data is a little bit compromised in that respect. Hopefully, we will continue to instrument these so we can monitor this in real time and learn more about the history of loading and ability to forecast in a statistically based fashion earthquake hazards. And so I'll just end with some summary of some observations. You can read them, I guess. The magnitude of the earthquake and the size of the tsunami was really unexpected based on 400 years of historical records. And so in these big subduction thrusts, we now are alerted to the fact we really need to look at these super cycles. That is, you have the 100-year cycle of magnitude 8s in Tohoku, but then every 1,000 years there's the possibility of one of these combined events, and that could have occurred in the past. This is a little bit speculative, but it certainly alerts us to that's a possibility. And the same thing could be other places as well. The earthquake was a compound event, I think I just said that. And so tsunami generation, we now know, is influenced by several factors. You can't just go by the magnitude of the earthquake. The Alaskan earthquake was larger than the two. More energy released in the Alaska event than the Tohoku event, but the tsunami in Tohoku was longer reaching and 4 times as high. So And then we also know from the Alaska event that the local possibility of submarine landslides and local tsunamis is also incredibly significant. So predicting tsunamis, even after an earthquake occurs, predicting the tsunami and where they could pop up is also incredibly difficult unless one had really high density real-time warning monitoring, like pressure sensors or sensors of seafloor of sea surface height and a real-time warning system. Maybe that's something in the future we should hope for. And I should just say that, you know, our observations finally showed, at least in one case, that the dynamic strength of the fault is extremely low, which really leads the mechanicists, the people that model earthquake rupture, to think, how can we possibly stop ruptures? Because once they get going, they become so weak that they just continue to go. And it means that stopping is probably a more challenging thing to explain than continued rupture for these really big events. And of course, Sumatra was ruptured, several sections that had ruptured independently before, but ruptured several of them all at once and ran 1,000 to 1,200 kilometers along the trench. So that's consistent with that. Is there a question?
What do you mean by co-seismic slip?
Co-seismic is the part, co-seismic slip, I'll show you this. This is an interesting result. Co-seismic slip is the amount of slip that occurs right during the earthquake. But it turns out that, although an interesting aspect of earthquakes is they're asymmetric. So before an earthquake, the amount of premonitory slip is very small and very local, which is a real difficulty in predicting earthquakes, or even recognizing by measure, even if you had dense measurements, recognizing when a big earthquake is going to occur. They start out like small earthquakes, and not like a big earthquake. But after the earthquake, after a big rupture like this, they continue to slip. They actually decelerate. So after they arrest, then they continue to creep, and it's in a decelerating fashion. So in the case here, like for example here, since in the last, now a lot of this occurs shortly after the earthquake, because it's kind of a logarithmic decay, but this is still creeping down deep. But even on the fault surface itself, it's expected that they continue to creep. So in the case of the Tohoku, where it ruptured 20 meters, like at the hypocenter, it continued to creep and accumulated, it was creeping at about 1 millimeter per day for several months after that. So that's the afterslip.
Aftershocks?
Yeah, they're associated with aftershocks, but it's really on the main, the aftershocks are usually all around, but that's actually on the fault surface itself. And we understand that pretty well. And down deep, this is thought to be creeping all the time, but right near the end of the co-seismic rupture, that is the brittle type of rupture, then that dumps its load, stress, it transfers it to all around the margins of that rupture, and it accelerates the creep down deep. And we've also, I should mention, in the last 10 years, we've also identified that and documented that earthquakes, we used to think of earthquakes as a binary phenomenon. Either they rupture quick, or they just creep continuously and steadily. But now we know that earthquakes occur at all different rates and at different manifestations. So in Japan and Cascadia, we now recognize very small creep events that have weird kind of low frequency, almost like vibrations or a tremor or harmonic tremor. And they're slip events that are taking place below the seismic zone at deeper levels. This is deeper into the seismic. So we're really still learning a lot about the way faults slip. But yes, that's co-seismic is what happens during the earthquake, and then there's additional slip. And in this case, 4 meters down here since the earthquake itself.
What's that slow event? Was that the one that went in front of Denali and the slow slip event?
Oh no, this is GPS data. This is also from Freimeller's group, and this is they're documenting that this is a portion right here where they documented an event that was not earthquake rates over many years, but in the period of time that we've had GPS, which is only about 10 or 15 years, there was kind of a big area that accelerated and decelerated, but very slowly, but a creep. But it was kind of like that's an example of really slow earthquake. It doesn't release any seismic energy because it's too slow, but it's seen in GPS data. And this kind of information is really important because when this slips, it also loads the bottom side of these stuck portions. So once we get, I mean, it's kind of a dream for earthquake seismologists and geophysicists to have really dense data instruments to monitor these things, because we're learning that we can learn a lot about the relative loading, and with fancy numerical models, we have a lot of potential to be more correct in our forecasting. Not prediction in the traditional sense, but forecasting of likelihood, or the areas that are more likely to rupture. And then also, if one ruptures, whether like if we have a rupture here, whether the neighboring sections are very prone to being triggered or not. These are things that we can hope for in the future, I think, with instrumentation. Yeah, this is the other thing about shallow slip. In the Tohoku event, we didn't recognize that. Now we've documented it, so that could occur. Certainly in Japan Trench, because there's the same kind of incoming stratigraphy in the subducting slab, but it's probably likely in other trenches as well. And then really this is that measurement about coupling between plates in the interseismic period that I've mentioned. The GPS is quite powerful. Yes, and I'm done, so I'm happy to take some questions. Thank you. And I probably went over, I apologize.
I just wanted to make sure that my understanding of earthquake magnitude was correct. So the way I understand it, magnitude 2 earthquake would be 10 times more powerful than a 1.
Actually, it's 30 times more.
30 times.
Yeah.
So then how much more powerful would a 3 be than a 1?
It would be 30 times 30, 900 times.
So when you're going from a magnitude 1 to a magnitude 9, that's got to be like hundreds of millions of
30 to the
times
9.
more powerful.
Yes, it is.
I thought it was 10, and I was like 100 million times more powerful. How can that be? But now it's 30.
Yeah. So now
I can't even deal with
we've
those
had
numbers.
various scales for earthquakes.
Mhm.
You know, Richter magnitude, and now we use the moment magnitude, which is more robust. It's really about the energy release. So the energy release is 30 times more. The magnitude of ground shaking is by factors of 10, I believe.
Okay.
So that's where the 10 times comes in. But the energy release is by factors of 30.
Oh my goodness.
Yes, a magnitude 9 is huge. And the difference between 9.2 and 8.8 is also very large.
I mean, you know, when there's even like a 1.4, you know, we feel it and everyone talks about it all day. And oh my gosh.
Yes.
Oh my gosh.
That's right. And the ones we're talking about are just these massive events. But don't minimize the impact of a 7 and an 8.
Yeah.
The Whitechurch New Zealand event just a year or two ago was a good example of that. It was only, I think it was magnitude 7, and it was devastating because of the location and the energy. Well, we now know that the energy radiated can be very directional too. You know, and that's another thing that can be forecasted. If the ruptures propagate in one direction, they radiate a lot of their energy in particular directions from the rupture. And if they rupture in the other direction, then they radiate in other directions. And there's, for example, in Southern California, they do scenario earthquake modeling. And if in the lock section the rupture initiates in the south and ruptures north, it's very devastating for Los Angeles. So rupture in the north and south, it's not so devastating. I mean, still significant, but so these are the kinds of things that we're learning and now able to model with good, pretty robust models about those kind of fundamental or general characteristics. The details are still there's a lot of details that we don't know and haven't worked out. And we're just like I illustrate, we are discovering things like this dramatic weakening we didn't really recognize that 10 years ago.
Yeah, with this new mapping of the loading across the whole shelf area, do you guys think that the release of the 1899 earthquake in Yakutat helped release ultimately the fault zone to the 64?
Yeah, well, I think the way the way that we usually talk about it is if you think of the earthquake cycle, and when I showed that diagram with the little spiky curves, everything is exactly the same and the same timing. That's of course completely wrong. It's not that regular. But what we think is when earthquakes do, of course their loading is steady and they do accrue displacement steadily, so at some point they are going to rupture, but the exact details. But what you can imagine is when a neighboring earthquake ruptures, it effectively transfers some load, which we'd like to talk about as advancing the clock. So it doesn't necessarily trigger it immediately, but it advances the clock. In some cases, a neighboring earthquake rupture, depending on its characteristics relative to the other usually not on the same fault, but if there's neighboring faults, sometimes earthquake ruptures can cause the clock to lengthen, that is, go back. But in many cases, it's advancing the clock, and particularly on these segment boundaries like that. So yes, the 1899 probably advanced the clock on that end, and in fact, the nucleation of the 64 event was on that end of the rupture, right? It was pretty much
Yeah, it looks like they
at
did it connected.
the eastern end, and then it was a kind of a unilateral rupture. And sometimes most times they usually nucleate in the middle and make a bilateral. So that would be consistent with that, although it doesn't. This could be coincidental.
Yeah.
But in the same token, the 64 event then, because it had been accruing a lot of displacement for many, many years, so when it ruptured, it probably advanced the clock on that section.
Do you think humans could ever reach an understanding of earthquakes that to the point where we could prevent them? Where we could say, okay, we see that there's a lot of pressure right here, let's release that pressure, no earthquake. We don't have to worry about it. Do you think they'll ever get there?
In the 60s, in the heyday of thinking that we were actually going to be able to predict earthquakes, and then we were humbled. Luckily, that was before my time, so I can't be held responsible, but I grew up being humbled. There was also ideas about earthquake control or engineering, and it was kind of that logic that, well, if we know it's going to go, we'll just trigger it before it loads up big and have a bunch of small events.
Yeah, like a domino
The problem
effect.
is that I don't have these plots where I show them to you, but if you look at the global release of energy, it turns out that it's dominated by a few big events because of this factor that a magnitude 9 is so much bigger than a 7. So if you were on the San Andreas and said, well, we're going to have a magnitude 8 here, so after the 8 event, we're going to just trigger a bunch, frack it, and we're going to cause a bunch of small events. But the thing is you'd have to have a magnitude 5 every day of the year for 100 years, and even then, the idea that you're going to be able to do that is just prohibitive. And the answer is no. It's kind of like controlling a hurricane. There's no way around it. This is Mother Nature. What we can do, hopefully, and it's primarily going to be through increasing our observation systems. We can be more educated about forecasting. And right now the cutting edge is to make models of multi-fault systems. This is being done in Southern California as we speak. And we know enough about earthquake physics that we can at least create a model so that we can update it. So when there's an event, then we can model that event and understand how it transfers the stress to the neighboring events. And eventually we can come up to where we know what the stress is everywhere, and then we can better predict when an earthquake occurs, how it's going to trigger the other ones.
So at this point, just everything that happens just adds to our understanding.
Yes, that's right. We pretty much learned a lot from every big earthquake.
Because like you said, we've only had like 200 years of proper
That's
history.
right. And so what we just are anticipating is that the magnitude 8 earthquake cycle in these subduction zones is about 100 to 150 years, but the magnitude 9 is much longer.
Okay.
And now we're realizing that the magnitude, in Tohoku, we had a magnitude 8 every 100 years, as we expected. And we thought we were relieving everything. And then all of a sudden a magnitude 9 pops up. So, so it's a very complicated and nonlinear system. Our handicap, I like to draw the analogy with weather. Weather is also a very nonlinear system, which means it has cycles, but they're never exactly the same. And then you can get these because of nonlinear effects and coupling and feedbacks, all of a sudden something can get quite big or quite small, and it's very difficult to predict. The difference and earthquakes are the same way, because they're governed by a number of processes and a number of different kinds of feedbacks.
Too many variables.
And there's a lot of variables. And so they do have these cycles, but they're never exactly the same, But the difficulty with earthquakes compared to weather is you're talking about the atmosphere, so we can see through it. We can send measurement probes everywhere. We can fly through it. We can monitor it throughout the volume that's taking place. In the solid Earth, we can't see anything except the surface of the Earth. So it's like we have a three-dimensional thing where all the action is down deep, and all we can do is see this two-dimensional surface to the displacements. And even then, we don't have that many instruments. Really, we have so few instruments. And so with time, we'll probably get more GPS instruments. We have a good number of seismometers out. So when we get more, longer history, better understanding, and more monitoring instruments, then we have a very good chance of advancing our ability to forecast. But it's never going to be solved, or it's never going to be.
You can't
It's
control
not,
it.
and it's probably never going to be predicted.
Ocean circulation modeling suffers the same drawbacks.
Yes.
Because we're remote sensing everything we do in the deep ocean. Only satellite imagery can give us a very surface phenomenon. So the atmospheric science is far ahead in the modeling because, just like you said, we can get more data through the whole atmosphere.
That's right.
You can see the profiles more readily, so.
That's right. Yeah, exactly. And in the ocean, there's some really deep currents that are pretty important.
Yeah.
So,
I had one question about the amplification of the wave, the tsunami wave. Is that very close to the continental rise where the amplification of the wave would occur normally when a tsunami would come in? When you showed that plot where the sea surface elevation suddenly just went up by many meters?
no. Okay, so if you go, I can go back, but you can also remember it.
Yeah.
Those are time plots. So those sensors are sitting on the seafloor. So as soon as the earthquake occurred, in their location, the land went down, and so the sea level started to rise from that. And then the areas that went up, that wave rolled in. So it rolled past this sensor. So that was the broad
Okay,
rise.
so that it was reporting something that waved as it came
in.
Gotcha.
So you're looking at the time.
So that's more typical of the tsunami, yeah, usually although it was deep water, the tsunamis, usually the surface expression is very low until it amplifies over
Yes,
the shallow.
if you look at the amplitudes on that, you'd see,
That was really an interesting
those
thought.
were, it's really fascinating data. I should say the Japanese, in their style of completeness, they are now along the entire Japan Trench, because they're worried about northern and southern segments, as well as the Tohoku segment. They now are installing a cabled network of hundreds and hundreds of instruments that include pressure sensors like that. And it's just unbelievable. It's what, of course, we should be doing in Cascadia. Cascadia had a super event in 300 years ago, and that's the interval that I think it ruptures on. And it's a big potential earthquake threat, which we should really be monitoring. Yeah, so this is, so if you look, this is offset, but you see this, the elevation, this is deep water. It's way out here. It's about halfway out. And so it's very deep water, and you see this is the earthquake shaking itself, and then the wave slowly rises as the water, as the wave, the bulk of the wave is moving inward.
About 11-meter wave, that's still pretty high for deep water.
Deep water 2-meter wave is very large.
Yeah,
that's
very
absolutely correct. And then this thing, it goes up to 11 meters.
Yeah.
Or well, it's 5.5, but that is.
Yeah, you take the 6.
Yeah, it's really
That's
deep
still
water.
high.
That is a very big wave. Yes. Yeah, I mean, it's just riding on top.
Usually when you're out, a tsunami passes under a ship, you don't even hardly.
Oh yeah, if you're on deep water, you don't even know. It's just a meter or two.
So that's very unusual.
Yeah, it's quite a remarkable record.
Yeah.
And then its ability to invert, just like they invert seismic waves to find the source of the earthquake and its characteristic, they can now invert tsunami waves. And they do tsunami scenario modeling the same way they do earthquake scenarios. We have these models pretty sophisticated. But in both cases, some of the details can be quite important. And so it's not, it's informative, but it can't tell us everything.
What do the two graphs represent, TM1 and TM2? I didn't get
This is
that.
kind of confusing. So there is a pressure sensor sitting on the seafloor. This is TM1 is right over in here somewhere, and TM2 is right here. So it's sitting right about here. So now most of the uplift is over here, okay? And it actually down dropping is over here. It's actually subsiding over here, and the uplift is out here. So the way the seafloor is raised up, so the sea level goes up with it, right? And then this is high. So now sea level over this whole region is several meters higher than the neighboring regions. And so then that wave starts to spread. It spreads out to sea and it also spreads inland. So right here at TM1, this is shaking, this is a pressure sensor at the bottom, so as the sensor was wiggled from ground motions, strong ground motions on the sea floor, the pressure varied. So this is like seismic waves, okay? And then this is a half an hour, okay? So then within 30 minutes, about 10 or 15 minutes, this wave, this big uplift, started to pass past TM1. So as the wave moves over, and so this is actually a time record. So after 20 minutes, it rises this much, and then after, let's see, well, what is this? This is actually half an hour. So these are 10 minutes, right? So 10 minutes, or 5 minutes, it comes up, and in 10 minutes, it's kind of stable, leveling off the way we would expect for a broad wave. But then all of a sudden, this baby kicks in. That's from this little business right out here at the trench. The big slip right at the trench really created a very short wavelength, impulsive wave that was riding on top of this larger swell. And so it just came in. And it's a very robust feature because you see at TM2, you see the same exact wave, but it's a little bit later in arrival as you would expect because it's closer to shore. And so they also have buoy data, but this seafloor pressure sensors are really important. So the Japanese, they're putting a cabled network that's going to go zigzag like this all over the seafloor, like this, with pressure sensors and seismometers and other things. And it's cabled, which means that they get the data real time, continuously, all the time. And then they're going to swing it out past the trench and look out at the outer rise. Because I didn't talk about that, but there can also be very devastating earthquakes out in the outer rise as well. Now, within the subducting plate itself, because the plate is bending, it can cause big normal faults. And they can be very, they are vertical, they're steep vertical faults, so when they slip, the seafloor really changes. So they can generate big tsunamis out here as well. So anyway, they have this, and they're going to do this not just in this section, but the section below that down towards Tokyo, and then the section, 2 sections up here. 4 times this length.
Did that black section slips seaward to the right?
Everything here is slipping seaward, right? And because of your earlier question, you say, well, what is the slope? The fault itself is inclined at about 5 degrees. So when you slip it seaward 40 or 50 meters, that means that seafloor is raising up about 8 or 10 meters because of the gentle incline. And not only that, then when you got to the trench, the seafloor itself is sloped. So when you translate it, you're not just raising the wedge, but you're also moving at 50 meters, you move the seafloor, which means at that point, the seafloor actually comes up as well. But anyway, so yeah, that's what the vertical motion is.
Increase the displacement.
Yeah, it creates vertical displacement is the key. Yeah. And, there can be splay faults, and that's a very important process because, there's the gentle basal fault. But if you have another fault that comes up like this and the displacement transfers up there, then it can cause a local uplift further inland. And in the Nankai, they think there's a really important active splay fault that's about midway. So in that case, and in the Alaskan earthquake, there's one that goes through Montague Island, and they know that uplifted more. So that can be one of these local effects. It didn't have to rupture the trench in Alaska. That about halfway out at Montague, that fault was going more vertical. So that causes local uplift, which also probably created some kind of a wave local on top of the broader wave. Maybe just not this dramatic.
So is it true that Japan is one of the most active earthquake areas in the world?
It is. It's very active. Did I take the, oh no, here's the plate tectonic map. I mean, it's not just the Pacific under North America.
They should just move out.
There are just, the Philippine plate. This is where the Nankai Trough is. And this one is, ruptured several times in the last 100 years. It also in a sequence, several earthquakes in a row. And it doesn't take long for it to recharge. So they're worried about it as well. And the effect of it on generating tsunami that invades Tokyo is quite obvious. As would be the southern section here below Tohoku. So after this rupture, the fear was that this section would also rupture because its clock would be advanced, as well as the one up here. And that's very close to Tokyo and could really be devastating for Tokyo because it's got a lot of infrastructure right at sea level.
Yeah, that's one heck of a place to build your empire.
Well, we do it too.
Yeah.
New York City.
We're thinking dealing with for how long?
There's a lot of things that
Yeah,
all
it's a
happen.
really old culture. That's the different, yeah.
It's really,
More development, we have more devastating they are.
yeah, Japan is like Alaska, really. It's got it all. It's got volcanoes, it's got
Whole ring of
active
fire.
tectonics and mass wasting, landslides. It's above ground and undersea, and tsunamis and earthquakes. And it's got a lot of deformation in the upper plate, just like Alaska does, like the Denali Fault and so forth. I mean, there's a lot of, I did put a lot of slides here. You guys are really very patient to sit through this. And I'll talk as long as you let me.
So much of it just flew right over my head.
There's some really amazing things that we're finding. This is a really quick and dirty representation of the Alaskan earthquake. And here's the Yakutat microplate. This is not even really considered a plate. It's actually an exotic terrain. It's a piece of continental crust that's been carried with the Pacific Ocean plate and now has run into the continent. Turns out this has repeatedly occurred in Alaska. In fact, Alaska's about half of it is built by accretion of small plates that get carried with the Pacific plate, and then when they get to the subduction zone, they don't subduct because they're too buoyant, the continental crust, and so they just get stuck on. So this is Wrangellia. This was a piece of continental crust. These sections of continental crust were carried from the southern hemisphere all the way up to run into Alaska. Carried sliding along these big strikes that transform faults. And so you can see the Chugach terrain is like this. And you see this pattern that they're kind of thin and then they wrap around. And you see this one, Chugach, and you see the Prince William terrain. And now here's the Yakutat terrain that's coming in, just like all these did before. And now it's running into the corner and it's getting stuck in there. And it's got a big thrust fault here that can release earthquakes. And then this section here where it is subducting under itself, okay, and then of course where it runs into the extension of the Aleutian megathrust here, which is obviously the large. So this is just fascinating geology, and it's all this business that makes the high mountain belts in your neck of the woods right here. There's this bits of continental crust running into the continental plate.
Wow.
Is it going to keep getting pushed up and sort of elongate like the others too then? Is that
Yep, it was probably going to do exactly the same thing. It's stuck in there. Yeah, it's a really it's just fascinating geology. This is people do all kinds of great things. They use isotopes and geochemical signatures and to look at uplift and exhumation, so they can rework the history of the Chugach terrain and the uplift in recent time. The last 5 million years there's been some reconfiguration. Things like this are going on. It's really amazing. This figure, I just have to show this. I came across this and I thought, what the heck is this? But this is where someone has mapped the Yakutat terrain, but also determined through seismology and deep seismic profiling, that's what these are, I think, has determined that actually it's been subducted this far underneath the megathrust. Okay? So that's pretty wild. And then this is the Pacific Ocean lithosphere, like this is out here, that it was subducted before this piece of continent came into the subduction zone. So it's in advance of it here. And this, of course, is normal Pacific plate being subducted down here. And then look at this. At this corner, here is this beautiful piece of Pacific Oceanic lithosphere, and now there is an incipient tear. Okay, and look at this. Oh, I'm sorry. Yeah, I went too far. Or maybe I didn't include that slide. I'll just show you. No, and I promise I'll stop. Well, I think I'll stop. Yeah, okay, I'm going to go backwards. Yeah, okay, so here's the modern seismicity. Here's the 1899 rupture that created the magnitude 8 in 1899 in the Yakutat.
So each point is an earthquake?
Well, this is the extent of that rupture, so to speak.
Okay.
And then, this is probably also an uncertainty. This is about the extent, I should say, this is probably the uncertainty of the location, but it's thought to be right here. And then this is that incipient tear. There is no plate boundary here, there's no terrain boundary. This is just pristine oceanic plate, but probably because of this complexity, it's starting to fault. And look at this lineation. I mean, this is definitely a crack that's growing in pristine oceanic lithosphere.
What are each of those data points?
This also, by the way, could make a big earthquake. You guys have it all here. Volcanoes, mountains.
So don't you want to move here?
Yeah, flying in, I'm just like, I'm in geologic heaven. It's like active tectonics and,
So each one of those spots is a recorded earthquake?
yeah, these are the
The
ones.
question is, would you live here?
This is not my first time to Alaska. I have relatives that live, my only cousins, my 3 cousins live in Anchorage and Eagle River and near Big Lake. And my
Much
aunt and uncle,
safer places, huh?
yeah, my aunt and uncle homesteaded in the early 50s, in the last homesteading act to get landed near Big Lake, near Wasilla actually, famous Wasilla. Now famous. And I had my first trip as a 14-year-old to Alaska to visit, just live with them for a summer in their cabin. And actually we took a kayak trip in Prince William Sound out of Whittier. We got a fisherman to take us on our kayaks out to Colross Island, and we paddled up and down Colross Passage. Yeah, and talk about young and ignorant. Man, we discovered tides the hard way. I don't know how my aunt and uncle would permit us to do that. My mother certainly wasn't, but she was in Southern California, so she had no clue. That wasn't the only wild trip, by the way. First of many. Thank you for your attention. You're very, very.
Thank you.